You can lean and go to sleep.
Okay, so thanks for staying until the last talk of the workshop. We are very happy to have Professor Adam Wierman from Caltech for the last talk. Adam has received numerous prestigious awards from multiple societies, IEEE Communication Societies, William Bennett Prize, ACM Sigmetrics Test of Time Award, multiple Best Paper Awards, teaching awards. We all know him for his influential work on data centers. Today he's going to talk about learning to control safety critical systems.
Thank you. And thanks for sticking around for the last talk. I really appreciate it. So please interject. We're a small crowd, so ask me questions as we go along. There's some new things here. So just a paper finished last night. I tried to put some of the results in here. So some of it's the first time I'm presenting. So please, if it's not clear, let me know and I'll go into the details. They're fresh in mind still. Okay, so this is joint work over a bunch of different projects in my group. And so these are some students and postdocs that have worked on things in this area. The boxes on the 4 on the left are people who have now gone on to other places for faculty positions, and the 6 on the right are the ones that are still at Caltech, and I'll put faces along projects as we go along so you can see who has worked on what. And then, yeah, so the motivation for this talk is kind of the motivation for a lot of the work in our group right now. A very kind of standard, stereotypical motivation right now that many of us could use, but to make it a little bit more precise, AI certainly has a huge potential, and in our group, we're really worried about sort of realizing that potential when it comes to resiliency and sustainability of network systems, typically infrastructure systems like transportation, electricity grid, and cloud computing. And the natural question, the motivating question for a lot of grants these days is, are AI tools ready? And of course, the answer is no, as of today, especially for these safety critical applications. And I think, my favorite picture highlighting this is this one. It's getting a little bit old, but I think it's still really compelling. It's, the stop sign on the left has a few pieces of tape, and to the vision recognition system, it's interpreted as a speed limit sign because of those pieces of tape. And that's, not something that can be explained very easily. This is a problem of interpretability in the model, and the ability to generate this sort of adversarial example for these deep learning tools should give you pause in terms of deploying these things in safety critical systems. So I like to keep this example in mind as a big motivation for our work. And then there's plenty of news stories one can come up with around failures of deployment of AI tools in these safety critical systems. And I think all that has happily culminated in a document that I think is actually really important that was released last week, which is an AI Bill of Rights. This isn't a Bill of Rights for AI entities. This is a Bill of Rights for how AI should be managed in our lives as a society. And so if you haven't read this yet, I highly recommend reading it. There were a number of academics, our peers, that were involved in drafting it and putting it out. And I think the first bullet point in it is maybe the one relevant for this talk. It says that we as people in the US should be protected from unsafe and ineffective AI systems in our lives. And right now, we don't have a tool set to do that often in terms of deploying AI. So I think it's really crucial. It's nice to see this formalized, and it's really crucial in terms of a direction to build safety, tools that allow us to get that safety from AI. And then you can see many of the other ones that are relevant to this semester here in these bullets as well, in terms of it's a good goalposts for us as a community. And to make this really concrete, so you mentioned that I work on data center design and sustainable data center design. So this is something that we've been working on for over a decade now. And for those who haven't thought about it, the sort of 20,000 foot picture of this is, if you want to make a data center sustainable and reduce their carbon footprint, then you want to manage workloads at the data centers in a way where you're running things more when there's renewable energy available and less when there's not. And you do this by taking advantage of flexibility in the workloads, on-site energy storage, and many other things in the design. And so Designing these systems is something we've been working on for a while, and in the last few years, it's really become a reality that these systems are out in the wild at most major, large-scale tech companies are doing something along these lines. This is a Google press release around their system, which is now doing this not just in local sites, but in geographically distributed ways. And I like to use this one here because Anna, who's the team leader, actually came out of this community for her PhD and her work. So it's a success story of someone from our community going and driving these things at the industry scale as well. But this is clearly a place where AI tools seem really relevant. You can predict when solar is going to be available, when's going to be available, when the workloads will be what, how much flexible workloads you're having, and it seems like that's got to be the core of this. You make use of that in these system designs, and within Google, DeepMind had a number of splashy press releases about the possibilities of doing this, reducing data center cooling bills by 40% using these deep prediction tools in these designs. But when you look at what's actually being released, not just at Google, but at other companies, what's used in practice, it's not these AI tools. It's all robust optimization-based designs. And the reason is exactly the motivation I've been giving. You can't afford to fail at scale in these situations. You need guarantees, so you can't just throw deep X at this stuff and hope that you don't get a bad scenario in your deployment. You have to do things with guarantees. And so to make that really concrete, this is now from simulation in our group where you take, our ML-based is a DeepRL-based tool for doing data center management. Non-ML-based is a robust online optimization-based tool. And here, this is distribution shift between training and test, which you can think of as the sim to real gap for these systems if you're testing things in the lab versus deploying it. And this point here at 0 is that it's less than 40% here, but is that significant win from using DeepRL tools in this space. And what happens is with a fairly minor distribution shift, you all of a sudden get massively bad cost compared to if you just did the classic non-ML based designs in this. So the x-axis here is distribution shift. So think of this as the error between the distribution you train the ML on and the real distribution of wind solar workloads that you experience. And so the scale here isn't very meaningful, but think of this as not a huge amount, like moderate difference. And then this is the cost. And so, this is bad because if you deploy and you're out here, you're giving up a huge amount compared to, your old robust tool. But of course, if things are working well, you want to exploit that gain. And so, big win if training is good, big risk if distribution shifts. What you want to deploy is something that looks more like this, where you get most of that gain, but you're still protecting yourself in the event that you're off if you have a sim to real gap that's large. Okay, so that's the goal in cartoon form, simplistic form. And so, in one sentence, it's can you get those guarantees that are required in order to deploy these things in safety critical systems? And in sort of Pareto optimality form, you can sort of caricature the current world as you have these black box tools, you have these traditional online algorithms. You want to expand that Pareto frontier by getting better, nearly that performance and better robustness than you can get there. And in sort of typical lingo, this is combining model-free and model-based tools to get the best of both worlds. And over the last 3-4 more years, there's a ton of work with a ton of different approaches going at that middle ground. And I put a few here. There's many more. I tried to include some things from people I thought would be in the room here for today. But this is a wild list where I can adapt to whatever the audience looks like. And so, but that's not what I'm going to talk about today. So today I'm going to talk about a particular way of doing this, which as in this semester we've heard a bunch of talks about, which is learning augmented algorithms. And for learning augmented algorithms, you'll notice that this changed from untrusted or from model-free, model-based to untrusted expert and trusted expert. And so this perspective is that you treat the black box AI as a expert that may be good or may be terrible, and you don't know, and you treat the traditional algorithms as trusted experts, meaning they come with a guarantee. If you always follow their advice, you'll achieve that guarantee. And your goal then is to use this to make sure you have a guarantee, but exploit this in case it's good. That's the goal. And the architecture of these learning augmented algorithms looks like this. So you have an input, you run the key thing here is that these are black boxes. You get your untrusted prediction and your trusted prediction, and you have no idea how those are coming to you. You just get those predictions. You plug those into some sort of meta algorithm, and that meta algorithm combines these two expert predictions to give you your action, and then you want that action to satisfy the best of both worlds.
This is like you want robustness and consistency.
Yes, yeah. So this is robustness and consistency. So I'll get to that in a second. And so the key algorithmic design question here is, how should advice be used? Do you switch between them? Do you combine them? That's the algorithmic question. And as was just said, the desiderata here are you want to do simultaneously get yourself consistency, which is match the performance of the AI expert if the AI expert is good. And that means that like if the untrusted expert is bad, this is sort of trivially satisfied. So this only binds only as tight when the expert is good. But then at the same time, you don't want to give up too much. And so you want a worst case competitive ratio. And ideally, you want that worst case competitive ratio to be sort of near the best competitive ratio you could get for the trusted algorithm. So you're not giving up too much. Yeah.
So are you doing that to us black box? Because in principle, you can think of a white box approach as well on the line algorithm.
So typically, learning augmented thinks of these things as black boxes. It's nice to, as go and get into this. So I'll come back at the end to some like gray box versions of this. But I think if you're truly white box, then you're in the sort of like combining model-free, model-based framework. It's a little bit, different. I like this. I mean, you're the core of it. I like this because you can really, as I'll say in a second. Actually, I'll say it now. Like we've been doing this stuff with companies, and there you think of the company having a team that is exploring whether this stuff is valuable, a team that's optimizing the current system. And now the CTO is making a decision about whether to switch to this. They're too risk averse to switch to it, but now they can combine the two things that those teams have done in a way, and then those teams can still work and improve what they're doing, and they can still just use this meta algorithm to combine. So this black box approach is really useful from a practical perspective in deploying these things. Okay, so this is by competitive guarantee. In the literature, there's often also other things that people care about. So smoothness means that, think of these as two endpoints. If your predictions are nearly perfect, if your predictions are terrible, the in-between is of course valuable. You want to have smooth performance in between. And then one thing that's actually been very important in our applications is frugality, or I guess Antonius calls it succinctness, where, and this can go both ways. It could be that your traditional algorithm is using some non-convex optimization that is really slow to compute. And so you can get quick machine learning predictions in between. Can you still guarantee robustness if you're not using the trusted advice as often? Or vice versa, maybe your model is huge and hard to, it takes a lot of computation to get an untrusted advice out of, and you can use that infrequently. How few can you get away with and still get good robustness and consistency trade-offs? So this has been a really important question for the applications we're talking about. But I won't talk about those today. Okay, so to make this really concrete, let me give you an example in the control space. So in control, the classic maybe dominant algorithm is model predictive control, which basically just follows the predictions in a certainty equivalent way. And then recomputes your actions. And so this is, to give credit, this is a physical deployment in our wind tunnel. There's a massive fan here that can do lots of crazy wind dynamics. And so you can be really unpredictable in what the wind dynamics look like. And this is Guanya thesis, who's starting at CMU this year, as I remember. And he's a photographer, so he took this beautiful picture of the infinity symbol being done by the drone. So I have to put that up there. But the idea here is, if you have high quality predictions, model predictive control works really well. If you give it, so that's consistency. If you have low quality predictions and you treat them as if they're true, certainty equivalent, you're of course going to do terrible. And so, you don't get robustness. And this is sort of the traditional view, like most kind of control algorithms in the space really can't do well in this space. And here the uncertainty is coming from like the wind dynamics. Okay, so Learning augmented algorithms, we've heard a lot about them this term. I think this is like the 6th or maybe 10th talk that has put up this web bibliography. If you want to follow the field, go to that website and you can see like the live update of papers that people are publishing in this space. There's a ton of different models. You know, I have added a couple since the last time I had this slide up, but I'm not including all the models that people have proven things here on. There's a ton at this point. And so my goal in this talk is to do a little bit of an overview, but do an overview in the context of a specific model that I think is a really nice place to show algorithmic complexity, algorithmic limits for learning augmented algorithms. And it's one that I think we haven't seen in this semester yet. So it's good for that reason too. And so we're going to do it in convex body chasing. And my goal is to tell a story of like the complexities of algorithm design and what you gain from added complexity here and what the limits are of simple designs. So what is convex body chasing? It's exactly what it says. This is a 2-dimensional toy example. So you start at some point, you're presented with a body, you have to choose a new action, which is in that body. You just care that you're in that body. There's no differential in cost depending on where you are in the body. You move to that point, the cost you pay is the distance to move. And then you're given a new body, you choose a new action, cost to pay is the distance, and so on. Okay, so it's very simple, clean to define, nice, beautiful theory problem. You have your constraints from your bodies to fit the theme of the workshop, and you have the costs from your movement. And the challenge here is because you don't know the future bodies, and they could be chosen adversarially, you don't know where to go in the current body. That's the challenge here algorithmically. And so it has a long history. I'm hoping that I get to it about connections to control, and robust control is the last 5 minutes of the talk. But there's a lot of applications to data centers in this, and a lot of the applications come from this can be really reduced to functionation, online convex optimization of switching costs, various online control problems. So algorithms that you design for convex body chasing can immediately port into these other domains fairly directly with fairly general assumptions. So there's been a lot of work by both our group and Alad Hassan's group on using these sorts of tools in those settings. Okay, so lots of algorithm progress without going through the who did what when of the sequence. This is state of the art. I'll be focusing on this D rather than writing the D root D log T, but I'd say root D is probably the right answer, and this log T is an annoyance, but it's a very hard annoyance to get rid of. And root D is the lower bound, and D is the dimension of the action space here. Little d is the dimension of the action space. And so, in a classical online algorithms viewpoint, it's kind of almost nailed, this log T being the missing gap. And it's a simple thing intuitively. You want to move, because you have to be conservative, the adversary can give you anything next. You want to move to some sort of notion of center of the bodies. And the notion of center that is right is the functional Steiner point, is basically the message to take away. And so as this indicates, this means that you're quite conservative. And if we come back and we think about what ML advice can buy you, the Steiner point is going to have you move to some sort of center. If you know what's coming, you can be extreme. And in this example, you move once and you never move again. And it's way, way better if the advice was good. But if the advice was bad, it could, force you to, go in the other direction, and now you have massive movement unnecessarily chasing around a spiral. Yeah.
One feature of this policy is where you want to go doesn't depend on where you start. Steiner point policy. So this seems surprising to an outsider. So do you have any comment on this?
It's the adversarial conservativeness, right? So if you do anything else, you can be exploited. The first results did depend on where you were. It was a greedy projection. Greedy projection can get you reasonable results in some situations, especially in nested bodies, but it's just not as good as this.
So what is the competitive ratio for greedy?
I don't remember off the top of my head. It's maybe even exponential in D, but I don't quote me. I don't remember exactly. It's been, we've moved on, so I forget the greedy competitive ratio. My cache isn't large enough. Okay, so the algorithmic question then is, if we're going to do well with this advice, we need to understand, when we should switch between them, how much memory we should use. All these are the questions that we want to answer in terms of using this advice. And so starting off, the way most learning augmented models start off is you first just do something naive in terms of switching algorithms. And the naive thing as a theorist is some sort of doubling algorithm where you play, if you think just a little bit, you realize you have to start with the untrusted advice, because otherwise your consistency is terrible, because you could just be off immediately and never recover if the adversary stops the instance there. So you have to start with the untrusted advice, and eventually you have to switch to the trusted advice if the untrusted advice is bad. And so you need some idea of when to switch. And the doubling trick often works well as a starting baseline for these algorithms. You travel some distance R. When you hit R, you switch to the trusted advice algorithm, then you do another R, then you double R and repeat. And this has the advantage of, if one is doing very well, you spend more time in it. If one is doing very badly, you spend less time in it. And so it sort of self-balances the exploration across the algorithms in a smooth way. And because you're doubling, you're never hurt too much from choosing the wrong one compared to your total aggregate cost. So this is the way that you do it, and just emphasizing the black box nature. I don't care what the advice is coming from in this style of algorithm. And then of course you don't actually choose R. You optimize this to bias, to balance your consistency and robustness. Something like this gives you a result in the body chasing space. Only in the nested case is it an interesting result, but nested means your initial body is big and everything else is nested in it as you go forward in time. And so there you can get a 1 plus delta consistency, and then you pay inverse delta in robustness. And then the D here is just from the best known existing competitive ratio here for in the Steiner point algorithm. And so this capital D is the diameter of the action space. Well, this will be an important thing. This is really bad that the diameter is showing up in our practical applications. We don't want diameter dependence, because if you think of the action space as being very large, then this hurts you a lot. Yeah.
So the robustness is over the worst input and also the worst line.
Yeah. So completely adversarial. Jointly, yes. Yeah. And so, I will do this only for the first one, but if we think of a practical perspective, just a sec, this is really nice, because now whatever deep RL you applied to make your predictions, all you had to do is wrap these 3 lines of code around it, and all of a sudden you have a provable adversarial bound on deep RL, whatever variation you were trying. And you don't have to reprove it. If you change what you're doing from a learning perspective, you still have an adversarial bound for it. So this is the power of these learning augmented algorithms. Yeah.
So D here means that all these convex bodies are picked in a compact set of radius of diameter D.
Yeah. Yeah. There's some ball over all of them that's diameter D. Yeah. Yeah.
And I
Yep.
forget the definition of robustness. Is it
Just competitive ratio, basically.
Is it the base competitive ratio, or is it with respect to the optimal algorithm, which was described?
So we actually prove it by comparing to the optimal algorithm, and then so the way that we tend to focus on proving these is this is bicompetitive to like an algorithm that's robust and to the algorithm that follows predictions, and then you extend it to the optimal with existing worst case results. Okay, so this was nested, and this is our baby starting point result, because I want to emphasize a fundamental limit here. And so switching algorithms are not enough in this space. You can prove directly that there's no switching algorithm for the general case that can be better than 3 consistent. And this is bad, because then you have to give up a lot compared to what your AI ML tool was doing. And the whole point of this is to nearly capture all the gain of them. So you really want 1 plus delta consistency with these algorithms from the perspective of exploiting the IL. So that's one limit. And then the other limit we can prove in this is you need to use memory. If you're memoryless, then you can't have any robustness guarantee, you can't have any consistency guarantee that is non-trivial. And by that, I mean, you can't have a consistency guarantee better than the competitive ratio you can achieve if you ignored predictions entirely. And so, this gives us some space to work for. You have to be adaptive to memory, and you have to do something smarter than switching if you're going to get a guarantee like we want, which would be a 1 plus delta consistency result for general body chasing. Okay, and so next try. So next simple try, and this is kind of common across learning augmented algorithms. You start with switching, that gives you a baseline to beat. Then you try some version of multiplicative weights or your favorite k-expert stack algorithm, and you see what you can get there. And in the multiplicative way, oh, go ahead.
So your possibility results are for the switching algorithm, the possibilities for any algorithm.
Yeah. Okay, and so multiplicative weights, this is a la like Plum and Birch. So it kind of actually uses off the shelf those, and this is due to Antonius in terms of result. But so I don't think I need to go over this. It's just multiplicative weights applied. So the result you can get there is this following one. So it's general. You apply multiplicative weights, you get a 1 plus delta consistency. This new is the aggregate prediction quality. So I'm not going to talk about smoothness, but this means you get smoothness too, because if that quality is good or bad, it sort of just degrades linearly with that. And this actually is a very general result. So it applies broader to metrical task systems, and results like this have been proven in other models as well. This type of model result is very common, but it has a annoyance here, which is that diameter is showing up, and it's showing up additively. And there's another sort of weirdness in the result, which you'd expect as you improve consistency, like you expect a 1 plus delta and then something over delta or something exponential in delta in the robustness. There's a 1 plus delta in both places, and that's because the delta trade-off is really with this additive term. As you improve delta, you pay more and more in the additive term there in terms of the diameter. Yeah.
The eta p inside the parentheses when it has 0.
Oh, so eta's, to think of it as 1 plus in the way I've written it. So like perfect is 1 and then 1 plus. That's why.
If for consistency,
you can imagine you can choose your delta and make it all the way go down.
There's a factor 4 there, I think.
Yeah, but you can counter that with the delta if you want. So if I had chosen a different delta, I could counter that 4. Or no, I couldn't. No, I couldn't. So maybe there's maybe I have a typo here. Maybe it should be a 1 plus. I'm not sure. Thank you. Good catch. This is a new slide. Yeah, another question. Or you, whichever one wants to go.
Okay.
So sorry. Your untrusted advice is that each iteration you get a point of where to go, right? Is that equivalent to just getting like a whole sequence of like convex bodies, or like is there like where the lower bound to the upper bound is?
I don't know. Yeah, I mean, there's some equivalence, right? Because whatever information I give, I will use it to just give me the next step. But whether there would be some way of getting a better robustness consistency trade-off from using that that other information, I don't think there's a result saying yes or no to that question. That's an interesting question. And what I'll say is, in general, the question of what the advice should be is a really interesting question in this space.
So you said memory is going to be important.
Yeah.
Makes sense. So this is not.
This is not very, yeah. So I'm doing this because it's common, not because it satisfies those conditions that I put. So
you're saying this is multiplicative weights without memory, and
well, it has memory, right? Because you're updating your weights based on the cost. So yeah, I skipped over this maybe too quickly, but you're updating your weights based on the cost in that round, which means that the weights have a full memory of the costs embedded into them, right? So like the whole sequence matters in terms of what the weights are today.
My mental model for memory good. I mean, if you switch between algorithms, then the state could be kind of hurting you on both sides. Is my mental model. So I'm not able to rationalize how this is solving that problem.
It's not solving that problem.
Oh, I see.
Right. This is a first cut. It's an off-the-shelf application of multiplicative weights, and it gives you something, right? It gives you a trade-off. And in some problems, this might be good enough, but in the body chasing context, this diameter and the sort of ends up hurting you a lot. And because most of the online learning things end up having the diameter assumption in them, it's a little sometimes hard to see how that's going to impact in these things. But yeah, I'm trying to go through that one quickly. So my goal here is to say like this doesn't work, so we can move on. I mean, it gives a nice result, but we want more than that. And so the next step in what you might think of is like we haven't used convexity really yet in either of the switching or the multiplicative weights. So let's use the fact that our bodies are convex. What that lets us do is, actually choose something in between and adaptively be in between depending on the cost of the things at the edge. This helps. And so this is one way of doing it. You can actually, through this, reduce the problem to an online algorithms problem called bicompetitive line chasing. So in bicompetitive line chasing, you always are choosing a point on a line, and you want to at every point have a competitive ratio that is bounded compared to both endpoints of the line. So that's the bicompetitive line chasing problem. And so you can use ideas from bicompetitive line chasing to get a result here. And that algorithm that I'm skipping over quickly gives you our first non-diameter dependent result. And so here now, even if the diameter is very large, you get a nice bound, you get a √2 plus delta, and then you pay your delta or your over delta squared here for the robustness. This is nice. The dependence on the diameter is gone, but it still leaves something, right? Because we're not getting 1 plus delta. So this says if you're applying this to your DeepRL, whatever, you're paying a √2 factor just because you're getting robustness, and you can't sort of trade off all the way down to getting the full value of the AI tool. So we want to get to the 1 plus delta, and so this motivates the question: is this a fundamental limit? The answer is no. It took us a while to get here, actually. And so we were able to, this is one of the new results from this week, is we were able to prove a lower bound here that shows what is possible to achieve. So you can be 1 plus delta consistent with a randomized algorithm here, but you have to pay exponentially in robustness to get it. And so, this one, we're not paying exponentially in robustness, but we're not getting the same consistency guarantee. If you want 1 plus delta robustness, you need to pay exponential in the 1 plus delta consistency, you need to pay exponential in the robustness guarantee. And this one, I do want to give a little bit of a sense of the proof, because the proof guides us to the algorithm. So the instance that you can construct to prove this has this flavor. It's a little bit more complicated to define, but so think of this as a cartoon of the instance, not the exact thing, but this will get across to the main idea. So think of there being some body here on a face, and the Steiner point is going to give you something in the middle, but think of whatever your trusted algorithm is doing, it's giving you something in the middle of that face. So the adversary is constructing this. And then the prediction is on the boundary. So that's the time 1, or at time t, this is what you're doing. The diameter of this is going to be 2 to the t. And then the next body is going to be such that the trusted advice doesn't change. It's just hitting, in a sort of different dimension. And the advice is going to now move by 2 to the t to a boundary of that new body. And that new body has, twice the diameter of the previous body. So now the diameter is 2 to the t plus 1. And so in that way, we're creating this spiral where the advice is moving further and further away from you, from the trusted advice each round by a factor of 2. And you can do this in a way, basically, and so the key property here is the cost of the advice is equal to the distance between the advice and the trusted suggestion each round. So that balance turns out to be crucial to creating the instance. And that balance is going to then give us the right way to sort of make decisions in the algorithm as well. And then, that just in case you're curious how this works, it's not Euclidean distance. That's, how we can make this work. The proof then ends up saying that, like we said already, you have to start by following the prediction. And eventually you need to move your mass back to that trusted algorithm because it's much better. But the way this is set up, you can never move more than delta over 2 back in each round. And this is the statement that requires most of the work in the analysis of the instance. And once you have that statement, that means that if you just take time equal to 1 over delta, you can only have moved half of your mass back from the untrusted advice to the trusted advice. And that means that your cost has to be at least 2 to the 1 over delta at that point. Yeah.
If my X domain is some bounded fixed thing, so this will work as my horizon grows, this will work for an exponentially small delta and then not work anymore, right?
Correct. Yeah. And so this is definitely like showing the benefit you get from having bounded diameter and a limit of what how bad this instance can be if you have bounded diameter. Right. So it shows why that's such a challenge to get rid of. Okay, and so that key property here is what guides us to the algorithm. And so this is the algorithm which Nico came up with a great acronym for, DART, Discrete Adaptive Robust Weight Transport. And so it's sort of in the flavor of the previous algorithm that I skipped over quickly, where if I didn't explain this case in that algorithm, but if your robust algorithm if your trusted algorithm is just doing better than the robust algorithm, you just follow your untrusted algorithm. If there's a decision that needs to be made, you're updating the probability of following the advice, the untrusted advice, with this ratio basically. And this ratio has that cost over the distance between them. And the motivation for that is exactly that condition in the lower bound argument. And that ratio turns out to be right. And then basically the other complexity in the algorithm, but this is sort of standard in a lot of Bubak's work and others, is that once you have these probabilities, you sample through an optimal transport plan that converts the previous probability of following the device to the new probability of following the device. And that sort of transport plan and that distance is very specific to get the cost to work out in this.
So this transport is for coupling the choice of this A or B from one step to the next.
Exactly. Yeah. Okay, and then I already talked about that. And so what's the result you get? Well, you get a result matching the lower bound. You get that you're 1 plus delta consistent and 2 to the 1 over delta robust, with the n coming from the that should be a D. This. And the really nice thing about this algorithm is the same algorithm. You don't have to make any adjustments to it. Works in both generalizations of body chasing and special cases of body chasing. You just need to tweak the analysis of the algorithm a little bit. So the same algorithm gives best state-of-the-art results for the bounded diameter case. It matches what you can get with multiplicative weights. It gives it for metrical task systems, which is a more general problem, this is the first one without the D. It gives it for case server. You get state-of-the-art results that are, instead of delta to the K, just linear and delta, matching lower bounds now finally there. And this one I'm really happy with. I don't know how many people are aware, but K-function chasing. So if you have distributed agents making decisions, chasing online optimization problems, you still get the same sort of results and the same algorithm applying there.
For your lower bounds, do you assume that the information that you're given is like 2 points, or do you assume that it's 1 prediction and 1 convex body?
For the limiting results, though, or for the lower bound, the lower bound is 2 points.
Okay.
Yeah.
And so if you have 1 point in the body, it's not clear whether
it's not clear. Yeah. And so if you change the advice that the algorithms are given, I think it's a really interesting question. Like, different advice should have different trade-offs, and there might be a better advice that lets you get around this exponential trade-off potentially. I really like that question. Okay, so now let me come back to our applications quickly. So in the, I'm going to do this really quick, but that goal was basically the result of running the algorithm in the data center case. And so you don't see that exponential trade-off in a lot of these distribution shift examples. And so you can really, give up a couple % with distribution shift and still capture the gain from the AI, the deep RL tool. In the data center case, you can do the same thing. This is a collaboration with a company in the sort of utility space. So you can do cogeneration for the grid, where you have conventional generation, gas and turbines, and you have wind and solar, and you're trying to manage them together. Same sort of thing. This actually does even better in terms of the robustness guarantee that you maintain while taking advantage of it. The drone trajectory example, you can do the same thing. And so here, this is the same animation I showed earlier. Now I'm going to change the right-hand side to use an algorithm that's a learning augmented algorithm specialized to control. And the red is what MPC, so I've made the predictions even worse. And the blue, you can see a little gap there, but the blue is really able to avoid the predictions that are bad and still get very good performance, even with terrible predictions. Yeah, so that's my first piece. Good, I have 15, I was wondering. So, okay, so I'm going through applications quickly. So now I've spent on this problem, but as we've been getting questions, there's lots of other interesting problems in learning augmented design beyond this. I'll come back at the end to a full list of some, or not full list, but a larger list. But I want to highlight one more to close my loop in this talk, which is around this box in the pipeline. So far I've assumed you know enough to run a trusted algorithm. And that's a big assumption in reality. So in reality, there's some system that you have a maybe flawed model of that you're running your trusted algorithm using those predictions of. So in reality, you need to learn the model to be able to compute the trusted algorithm in the first place. Otherwise, your guarantees for this are all useless, to begin with. And so to make that really concrete, we'll look at a control example, and then I'll actually connect this back to body chasing in terms of the algorithm we use for this control example. But so the results here hold more generally than this, but I know this isn't a control audience, so I'll use the simplest model here. So this is just a linear system, time invariant. So we have our dynamics, our A and B. W is our noise. I'm emphasizing it because we're going to talk about adversarial and stochastic cases here. And just quadratic costs for now. So just LQR. Now, if A and B are known, then I can, synthesize a controller with robustness properties, huge literature doing this, and then I can plug it into meta algorithms, and I can design a meta algorithm that's specific to control, and I can give you robustness and consistency guarantees, and that's what these people did in a couple papers. So control case, if the model's known, we can do sort of the version of the story that we just talked about. But A and B aren't really known, right? So you have to learn A and B. And so in that case, now all of a sudden you really care whether noise is stochastic and adversarial. Since we're in the safety critical world, we want to think about the adversarial noise case. And that should seem like completely intractable, because how do you learn A and B if your noise is adversarial? It doesn't pattern match, right? And so let's come to the stochastic case first, and we'll learn something, and then we'll go back to the adversarial case. So in the stochastic case, there's been a ton of work on this learning to control over the last few years by lots of very smart groups. And without going through all of it again, summarizing state of the art, there's a really nice paper this year at Colts by Shaheen, who's at Caltech working with Babak Hasibi, where you combine Thompson sampling for exploration with linear regression to fit the A and B, and you get root T regret, even without knowing ahead of time that there exists a stabilized controller or controllability assumptions or things like that. You get it very generally. It's a nice paper if you haven't read it. But the thing I want to focus on is this n, which are the dimensions of the A and B. You have exponential dependence in that. And this is not like a drawback of their algorithm, because if you want to learn A and B, you need at least order n samples, which then means you're going to suffer in your state norm as you're taking those samples, which means that you're going to have at least 2 to the order n regret for anything you do if you're learning A and B. So this is sort of often viewed as just an unavoidable issue there. But do you really need to learn A and B? You certainly don't need to learn the whole thing. If your system is self-stabilizing, you don't need to learn anything. If all you care about is stability, you just run it. You don't care what A and B are. And if it's nearly stable, you shouldn't need to learn very much to stabilize it. And so we've I think this is a really motivating question. We have a first paper on this that's going to be at NeurIPS this year that gives a cut at it, which gives an algorithm that can stabilize the system after order k samples, where k is the number of unstable modes of the system. And so instead of depending on the system scale, you just depend on how unstable the system is linearly. And so this then gets you a stable controller, and then you plug in all the results about learning low regret, and you can have a pipeline that learns low regret without nosing stabilizing, and can do it quickly if you have a system that is nearly stable. So this is, I think, a good start. And now I want to come back to the adversarial case, because this now intuition says we don't really care about learning. If we care about, if all we want to do is stabilize the system, we just care about knowing enough about the dynamics to carve out the unstable modes. And that's now something we can maybe do in the adversarial case, even though we don't have any distributional assumptions. And so in the adversarial case, now we're going to make use of body chasing to not do learning, but to do consistency chasing of the model. So what does that mean? It means, I'll use the drone example. So we're trying to track some trajectory within some safety region. So we imagine a priori there's some set of models that could be true for the system. So here we'll assume that this has a bounded diameter because we have some idea of where the system might live. We just start with an arbitrary choice of those models, maybe Steiner-Kreuz, maybe something else. And then we synthesize a controller as if that was the A and B for the system. Okay, so that we can do with standard control theoretic techniques. Then we run that system. We run it for a while, observing the system's response to it. If we ever get to a point where we might run into some sort of safety issue, we stop it. We then take that batch of points and we update the set of models that are consistent with the data we've seen about the system. So in our model space, that means we look at a nested convex body. And so now the set of models that are consistent with what we've seen is a nested set of our original set. So that rules out our current model because otherwise we wouldn't have been in an unsafe region. And so then we choose a new point within that nested body. We synthesize a controller based on that. We run the system again. When we get to a point where something went unexpected, we know that our model was invalid. Our model wasn't consistent with the system anymore. We update our set. We look at a new convex body. We keep going. So that's the algorithm. So we're using body chasing to chase consistent models for our control system. Now, the result you can prove, combining everything I did in the first part with some control theory for doing the sort of, you need not just, you're not, I'm a little simplifying here, you need to synthesize an optimal controller with a little bit of robustness. So an optimal robust controller here. And so you need to put those two things together. And what you can prove then is this guarantees stability of an unknown system, completely unknown, no assumptions on it, on a single trajectory with a finite mistake bound. So there's a finite number of steps here where you're going to need to recompute and risk going out of your safety system, your safety region. And so this is the first result that I'm aware of for the adversarial assumptions here. And I've explained the simple version of it. This applies to time-varying systems, adversarial disturbances, and it applies in distributed agents, where you have agents distributed in a network doing distributed control, where there's communication delay on the information of the action and the response of the system between agents. And so we can do that because we can take advantage of system level synthesis SLS results in the control community, which has kind of happened in the last few years. And so, empirically, what does this mean? This is a simple single agent system right here. But you take, this sort of algorithm and you compare it with like, a sort of exploration and linear regression style system ID-based approach, and you avoid that massive jump at the beginning because you're not trying to learn the whole system. So you don't need to explore all these states to learn A and B. You can just, move only if your consistent choice causes a problem. And then we've applied this now in the smart grid setting to do voltage control. And so the story here is you have a grid, some part of the grid just failed, so you don't know your new network model. So you have to update your controller based on this new network that is there. You need to do it quickly, otherwise the cascade is going to fail. This blue is what happens if you kind of do a new estimate, your controller is wrong. The orange is what happens with consistent modding chasing. Anything that goes past this region means that you have power outages. And so we're able to stabilize without outages, without knowing anything about what the new network is. Only that a line failed, so that we have a nested model. Okay, so that's it. Sorry, my phone is buzzing. Okay, so that's the last result. Did anybody want to ask a question about that one? Before I go on to conclude. Okay, so the idea today was to give some idea of algorithm design and fundamental limits of learning augmented algorithms using convex body chasing as the example. So I talked mainly about how to switch between them, how to combine them, memory versus switching algorithms versus taking advantage of structure. And I gave one example of how you can apply this stuff on top to sort of learn the model to be able to even have the trusted expert in the first place. And I think this has a nice nested doll type story, because now in using the body chasing, you could actually use advice on what the model was from the Thompson sampling type tools, which then you could apply the robustness and consistency results in learning the model, so that then you could apply the robustness and consistency results. And so there's a nice nested application of these results to even learn the model that I think is pretty exciting. But then some of you have already been asking the more general, I think the big open questions in this space, which are, I think the biggest one maybe is this one. This was all for one version of what the untrusted advice was giving you. It doesn't have to give you a prediction of the action. It could give you more information. It could be, in our case, it could be predicting the bodies. It could be giving you a look ahead window of bodies like MPC usually takes. It could be predicting uncertainty about the action in addition to the action and giving you that uncertainty quantification. One that we're really interested in is, if you assume this is doing some sort of Q learning, now you can actually feed the Q function to the meta algorithm, and that gives you a lot more power. And so we have one result that we're working on there that does that in the control context. But I think that's an idea that Ankur Moicha did at Colt this past year as well in a different context. And then here another one that I think is really interesting that we're spending some brain power on with Chalet Ren is the idea of everything I've described, and most of the literature views the ML black box as static. It doesn't improve the ML through the process of applying the learning augmented algorithm. And that training should be happening through the system as well. Can you prove results then about learning within the context of the online problem, and how does that affect what sort of consistency robustness trade-offs you can prove? I think that's a really interesting question. All of these things kind of add complexity beyond the first wave of results looking at multiplicative weights and switching algorithms. There's a lot more you can do if you take advantage of these other aspects of the problem to get really sophisticated things and push the fundamental limits that are sort of starting to be understood for these problems. And then I guess coming back completely, smoothness, frugality, memory dependence are all really interesting questions. And then another one that I haven't seen much on, especially when you start to look at the ML model being trained online, is average case results about learning the correct action during the instance as well. I think we're really interesting to try to get into this. Okay, so here's references from our group in addition to the ones that were in the talk for other groups. Thank you. Yeah.
So you have this block diagram. So I'm struggling to map this diagram to the example, to the case of the LQR problem.
So the last case was only how to learn this model.
Ah, okay, it didn't fit in the.
It doesn't fit in, it's the question of, if you're actually deploying this stuff, you can't assume that the model is known a priori. You have to learn the model, and you maybe have to do that online as you're deploying this sort of thing, and you still want to maintain those guarantees.
Got it. Then one more question is, you talked about the stochastic case initially, and then you cited the work of Hasibi.
Yeah.
And then, so I didn't get the difference, how that work compares to yours.
So the Thompson sampling work assumes distribution, right? Assumes stochastic model. I guess which version of ours, the K versus N, or the adversarial versus stochastic? So the Thompson sampling is looking at Yeah, so it's still looking at regret. This is looking at stability, so that's one difference. So learning just a stabilizing controller, but that's a sort of superficial difference, because once you've learned a stabilizing controller, then you can apply whatever you want to get regret bounds after that. The key difference is here, our goal was to not have dependence on n. So here you're learning the whole A and B to get low regret, and because you're learning the whole A and B, you have dependence on the size of the whole A and B. Here we're saying that we can learn with rate dependent only on the number of unstable nodes. And so if it's very unstable, k could be n, but in many systems, k is going to be a small constant, and so this is going to be, order of magnitude faster.
Regret appears to be more stronger.
Yeah. Yeah, definitely.
Okay.
Definitely.
So what you're saying is by changing the goal, you can make it much faster.
That's one interpretation, but I'll add on to that. That's a little bit of a false distinction, because I'd say there's many regret algorithms that start from the assumption that you know a stabilizing controller. And so you can just add the next step of the pipeline to I know a stabilizing controller, and then you run any of those algorithms and things work well. And because you have a small number of unstable modes, those will work faster than if you start from this perspective and don't know the number of unstable
So in that case,
nodes.
can you actually prove this, that if you use this algorithm and then put a different regret algorithm on top, can you?
We haven't proven that. So you would need so the parallel to this, which somebody should prove, maybe us, maybe somebody else, is that if you know there's a small number of unstable nodes and you know a stabilizing controller, you can have regret that's independent of n. That would be a very nice result. And so empirically it works. I'll say that. But yeah, that's an open question to sort of do that, to take a result like this and do it for regret.
You think your algorithm, do you think we know if they have smoothness, or do you think you need another algorithm to achieve smoothness?
For the MTS problem?
Yeah.
Submitted it yesterday. I don't know. I don't know enough to say concretely. I would expect that it would get smoothless though. If you asked me to bet right now, that would, I don't know what the odds I would give are, but it would be on that side. Other questions?
What was the average case that you were mentioning?
Yeah, so imagine, if you're gonna do, if you're gonna answer this question, where the model's trained on line, you're gonna need some stochastic assumption on the instance that is arriving to be able to start learning. And so then you have the opportunity to say, is there an average case version of consistency, for example, that you can prove? Learning rates for consistency, and that would depend both on the meta algorithm and the learning you're doing here. And I think those are very interesting, because really, I mean, consistency is a very beautiful way of defining, but in some sense, the consistency a learning person might want is one based on average case results, because you're designing the learning algorithm under some assumptions on the instances. And so under those assumptions is the space where you really might want consistency. And that's a different constraint than the adversarial notion of consistency that most of the users focus on. Okay, thank you. Thanks for staying to the end. Since I am the last one up here, I guess it's my job to thank the organizers as well. So thank you for a great program.
Thanks, Balu. I'm running for a meeting.
Thank you.